Hi, I'm Bruce, and welcome to the Baptronics Mountain Labs here in Colorado. I am very proud to demonstrate my top of the line Fluke 1953A. This is a real beauty. It looks really nice, it's in beautiful shape, performs like a champ, got some fantastic features. She totally would throw you. You wouldn't hardly believe the age of this unit, and yet it's still in fantastic shape. The 1953A came with, I think, four different basic choices for your time base. This particular unit used the top of the line time base, and we'll take a look at it in a couple of minutes, and we're going to demonstrate what it can do for you. But it will give your bench the capabilities of something near a standard. I mean, when we get done calibrating this to the rubidium, you'll be about as accurate as you're going to naturally be. And then I expect that this crystal oscillator is going to maintain that for a good many years. And another feature, the basic unit, I think, was capable of measuring up to 125 megahertz. And then you had some add-on features. You could get a 520 megahertz add-on, and we've sold one of those here in the past. And this one has a 1000 megahertz, 1 gig add-on. So not only do we have something that has a really stupendous time base to work with, but we also have an extended range that'll get us up to the gigahertz, all in a pretty package. So let's open it up. We'll give you a quick tour of the internals, and then we're going to run it through some tests. Give me a minute. All right, so we've opened up the lid on the Fluke. And we're going to give you a little quick tour of the interior here. First off, this right here, this is our Oven Air, the top of the line Oven Air 10 megahertz oven crystal oscillator. It was the best provided for this unit. The Oven Air OCXO in this unit has an aging rate of plus or minus 1.5 times 10 to the minus 8th per month, and a temperature stability of plus or minus 2 times 10 to the minus 10th over a 0 to 50 degree centigrade temperature range. This gives you fantastic stability, and when properly calibrated, it's going to give you fantastic accuracy. It's going to give you a bench standard. It really will. I'll point out a couple of things here. We have circuitry back here to give you the fine adjustment for the frequency calibration. The calibration for frequency itself is right here on the side of the can. You remove that plug, and there's a screw in there for that. You have to be very careful. Best to remove that plug with the power off, then put the power back on. You don't want to drop that metal screw in there and short something out. Just a tip. The unit used to have a remote control, a basic remote control board in here. There was an option for that. The remote control board was completely gone. I removed it so that it wouldn't impede the operation of the Fluke. I did a little minor repair on the Fluke, but she's in great shape now. The 1 gigahertz extension card is here. We have rear inputs and outputs, front inputs and outputs, and then you see the fiberglass boards, first class traces, beautiful workmanship. All in this beauty. So let's put her back together and run it through its paces. All right, we have ourselves back together. And one of the first things I want to point out here is you'll see that we have a display of 1,000. I have my function is right now totally clockwise. I'm in the self-check position. The unit was turned on roughly an hour ago. And I have my range in its fastest position. And I'm displaying 1,000, and it would be 1,000 kilohertz. What that's displaying is the internal 10 megahertz oscillator, and it's counting the frequency using this range and displaying then the 1,000. So we've got 1,000 times 1,000 times 0.1 millisecond. We're going to get 10 megahertz as a readout. If I was to go to 1 millisecond, then we've got 10,000. 10,000 thousands would be 10 megahertz, so that's good. We go to range position 3, 10 milliseconds, we got 100,000. 0.1 second, we get 1,000,000. So if I was to go 10 of these seconds, or 10 times 0.1 would be 1 full second, you would expect to see 10 million. And then 1 full second, we add another 0 to it. So there's 10 million. And then if we go to the 10-second period average, we give this counter a chance to count up for 10 full seconds. And we're going to get 100 million on the display, which is the maximum display. So in effect, there we go, 100 million. What we've done is we've checked all of the ranges. We've checked the basic function of the counter. It's displayed the frequency. We've got the time base. It's a good check. Handy little thing. If something was to go wrong and you're wondering what's happening internally, well, you check to see, am I doing the same on all the ranges? Am I getting any kind of a count at all? You know, gives you a start. So this unit is called a universal timer counter at the time that it was sold. What do they mean by that? Well, to be a counter, it's just a frequency counter. Measure frequencies. If you are a timer, then you can measure time intervals. Universal counter timer, you can measure periods, you measure frequencies, you can totalize, you can do a lot of things. We're gonna talk about that right now. Functions. I have an A channel and a B channel. Frequency of A from 0 to 125 megahertz goes right in on here. I control my trigger level with this control right here, and we see the trigger status light come on. If I put myself into a preset position, that balances the input so that we're essentially at 0 looking for the smallest signal coming in. We can go plus or minus on the slope, so we can look at the positive peak and count those. We can look at the negative and count those. We got AC or DC connectivity, times 1 or times 10 attenuation, as well as the trigger level. Then we have channel B. Channel B gives us the capability of doing a number of functions involving like ratios and time intervals. Channel B handles from 0 to 25 megahertz. And we can either separate the commons on these or we can combine them together just by flipping the switch. Channel C allows us to read up to a gigahertz, 50 ohm input. We can measure the frequency ratio of A to B. So let's say we put a 100 megahertz signal in on A and we put a 25 megahertz signal in on B, then we're going to get a ratio of 4 to 1. If we were to put, say, 10 megahertz in on B and we had 100 megahertz in on A, then we're going to get 10. You might get a 1 to 1 if you had 10 and 10 on both of them. So that's the idea of the ratio. Then we can measure the period of A. Period gets utilized most commonly when you're dealing in the lower frequency ranges, below megahertz, say. Uh, you'll have fewer digits to display in the frequency counter because you're going to be counting, pulses coming through. And if you are looking for a small period of time, then you only get a limited number of pulses representing a megahertz or less. Let's say we're measuring 10 hertz. That'd be a good example. I put myself on the 1 second gate time, and I get a count of 10. Well, that's good, but that's not a lot of definition. If I put myself on period, I could have 9 decimal places worth of period information, and truthfully probably only 4 or 5 decimal places would be what I would want to use, but that's where the period comes in. I mean, you get a whole lot more resolution. Divide the period into 1, and you've got the frequency. So it's a roundabout way of getting frequency. We have time intervals of A to B. So when an event happens on A and then it counts, that starts the counter. When the event happens on B, it stops the counter. And you measure the time interval. I'm sure you could find a use for that, say for races, or maybe measuring pulses or something like that, pulse trains. And then we've got A gated by B. So whenever B goes high, we start counting, and when B goes low, we stop counting. So we could utilize different pulse times to measure what's coming in on A. And then finally the self-check. And then we have 6 gate times from 0.1 millisecond all the way up to 10 seconds. And we have, because we have the top of the line OCXO in here, we have a power control that allows us to go into standby mode. That shuts off most of the functions of the counter, but the power to the OCXO still connected. The OCXO is still warm, and therefore when we go back online, when I turn it back on again, I'm automatically going to be at my most stable point, because I don't have to go through the warm-up period again. So let's go ahead and put this beauty through its paces and see what it does. Okay, well, I have the 10 megahertz output of the clock running into the D channel on my analog scope up here, and I have my 10 megahertz signal from my master oscillator, which is coming through my PTS 500, coming in on the A channel. And then what I'm doing is I'm attempting to produce a Lissajous pattern in XY, and the object is to stop that pattern, or get it as close to being stopped as I can get it. And we're pretty close to being there right now. Just ever so slowly moving. We're out less than a fraction of a hertz. I can get her to stop. Well, there it is. That's the Lissajous pattern, where she's almost standing completely still. There's still some movement here, but it's much less than what the display, which right now is, the display is showing a solid 10 million.0. So we're in sync with the bench oscillator here, which is in sync with the rubidium. And we've calibrated this unit to be within a minute fraction of a hertz to 10 million. So we're calibrated. Okay, I decided to connect directly to the rubidium source. And we're looking at the Lissajous pattern formed against the rubidium. And we can see we're in lock, or we're locked to the same frequency. The rubidium is in lock right now. We've got a green light to go. And we're displaying 10 million with no residual at the 10th. So we're better than a tenth of a hertz at 10 million. So there we go, right against the rubidium source. My bench is calibrated well too, so there we go. All right, well, we've got the Fluke1953 back together, and we are measuring on the C channel at the moment, frequency C coming in. We're on the 0.1 second range. And we see we've got, let's try that again, 999,999.59 kilohertz. And what that is, that's a gigahertz. That's 1,000 megahertz, as provided by my 8640B signal generator. And it's telling me that it's putting out a gigahertz to 6 significant figures. So what it thinks is a gigahertz is being measured by the Fluke. So that'd be 999,999 kilohertz, excuse me. But it's not lying to me in terms of the figures. It is a gigahertz within that 6-figure range. I'm using a Raycal doubler on the output of this thing, and I'm in the extended mode, so I can read the megahertz, or gigahertz, excuse me, as registered on the frequency meter. And on my bench counter here, my Philips, I'm getting the same kind of reading, 999,999,999.99964 megahertz. According to the Philips. Okay. We've taken the 8640B as high as it'll go. Looks like a 1.09934 gigahertz, or 1,099.34 megahertz. And we are reading a 1,099.3396. And on my Philips, I'm reading 1,099.3396. So we're able to read more than a gigahertz. We're doing it right now. So let's go ahead and step this thing down. All right, we should be reading about 600 megahertz right now. And we've got 599,999.8. Same 0.8. 600 on the 8640B. So, okay, well, now that we've seen that the unit can measure more than a gigahertz accurately, what I've done is I've switched myself from the 8640B up to this PTS 500. PTS 500 is going to give me a very nice platform with which to choose some particular frequencies and step her down. And we can watch this thing go in incremental steps. And I just think it's really interesting and gives you a good idea that we're reading accurately. Right now we have 400 megahertz coming in, and could increase the range time a little bit, the gate time, and pick up another decimal place. So like right now we see that we're running 399,999.99, and we saw it swing to 400 there. We're using the internal oscillator, so we expect to see a little bit of a difference, minute difference, but a little bit of a difference in the reading here than what I'm going to get on my generator or my Philips, which is being run by the generator, time base wise. But we're getting the 400 megahertz. All right, now we're going to step her down. Let's go to 300, 200, 100. All right. And that'd be 190. All right, let's go to 90. 80, 70, 60, 50, 40. All right, at this point, I should change from my channel C input, which is rated from 50 to 1000 megahertz. Go back to the A. All right. And put myself on frequency of A, and I see I've got 40 megahertz there. 30, 20, 10. All right. There'd be 9, 8, 7, 6, 5, 4, 3, 2. It'd be 1 megahertz. 900 kilohertz. I'm going to be able to go down to about 600, then I'm going to have to switch to a different generator to pick up the low end. It's 800, 700, 600. Alright, so we just went from about 1100 megahertz down to 600 kilohertz, and we measured it perfectly on the meter here. Very nice, very responsive. Let's see. I'm going to switch myself over to this Hewlett-Packard 3320B, which is meant to run from 1 megahertz down to a fraction of a hertz. Let's see, we want to roughly a megahertz on the frequency generator, and we see we have 1000.02 kilohertz here. I could try and zero that in just a hair there. There'd be there's 1000 kilohertz. All right, and let's go 900 kilohertz, 800, 700, 600, 500, 400, 300, 200, 100, 90. Let's turn our time base up to a second. Okay, that's good enough. Here's 80, 70, 60, 50, 40. Remember, this is kilohertz. 30, 20, 10. All right, we're going to step. There'd be 9, 8, 7, 6, 5, 4 kilohertz. 3, 2, 1. All right. It'd be 900 hertz. 800, 700, 600, 500, 400, 300. Now we're updating once a second because we're on the 1 second range. 200. But that's limiting us to one less decade of count, which we could pick up if we went to the 10-second average, but then it'd take 10 seconds. And we're going to be forced into that in a minute. There's 90, 80, 70, 60, 50, 40, 30, 20, 10. All right. 9 hertz. 8, 7, 6, 5, 4, 3, 2, 1. Now we're reading on AC right now. I could go to DC, and I think I'm going to do it. All right. And let's see how much lower we can go. All right, we're at 0.9 right now. We're going to go to the 10-second average. I'm sorry that it takes so long. We could go to period. We could do that in a little bit, and that would be a lot more responsive. But there's 0.9 hertz. There's 0.8. Gonna have to wait. Point 0.8. Let's go to 0.6 or 5. Let's do 0.5. See if we can get 0.5. There's 0.5. It's amazing. 0.3. Point 3. 0.2. 0.2. 0.1. Be amazing. Oh, wow. 0.1. So we're reading an input of 0.1 hertz right now. We're using the 10-second range so that we can see it. But there it is. We've gone lower than my Philips can handle. Well, I'm not on the 10-second range. I could actually probably pick it up. But our light is telling us that we're at 0.1 hertz on the 3320. We see 0.1 hertz on the Fluke 1953A. Beautiful. All right, so we've gone from 0.1 hertz all the way up to 1100 megahertz, or 1.1 gigahertz. She did it. Well, let's take a look at some of the features. Okay, I still have the 0.1 hertz signal coming in, and I've put myself now into the period of A mode, and I've moved my my gate time up to the 10 to the 0 period averaging gate, so that's, well, it's a 1 second gate, but the unit is going to take some time, and it's going to count the number of either microsecond or millisecond pulses that it can feed through in that gate time. And we're getting right now a reading of 10,026.7254 milliseconds for a period. So if I was to divide 1 by, instead of 10,027 milliseconds, let's make that 10.02789 seconds. So divide by 10.0273278, and that tells me that I have a 0.099727466 hertz signal coming in. 0.0997. That's very, very close to my 0.1 that my Hewlett-Packard thinks it's cranking out, and I'm sure that's what it is to the best of its ability. This gave me a heck of a lot more information for my frequency calculation, or for my frequency, than I would have gotten directly. If I'd measured frequency directly, we saw earlier, the best I can do was to get one significant figure in 10 seconds. So in 10 seconds here, I'm getting, I don't know, 9 significant figures. So it's pretty remarkable. Let's go ahead and turn this up to, let's make it interesting. Let's say 3 hertz. All right, I'm on 3 hertz, and I've got 333.33. Yeah, it's bobbling a little bit in the bottom end. 333.3 milliseconds. So that would be 1 divided by 0.3333. 1 divided by 0.3333, and I get 3.0003 hertz. So my period is working, and I am reading. I'm resolving the period of these low frequencies. And this thing, I think, can measure period accurately up to about 2 megahertz, something like that. And then you got to go back to frequency again, let that take over. All right, so there's frequency of A. We've looked at frequency of C. Let's take a look at the frequency ratio of A to B. It's going to give me a minute to set up, and I'll be back. Okay, I have a signal coming in to channel B on the 1953A, and it's right now, I'll just go ahead and I'll tell you, we've got a 50 hertz signal coming in there. And then from my PTS 500, I have a 10 megahertz signal. You can see that the 10 megahertz is showing on my Philips coming into channel A. And we're in the frequency of A to B, doing the ratio. So the ratio of A to B right now would be a ratio of 10 million divided by 50. And right now what I'm seeing is a reading of about 200,000. So that's about right. I'm in my fastest gate mode right now. If I was to step her up once, we get an update roughly once a second, and we see it even out a little bit here. It's about 200,000. So if I knew the frequency was 50 hertz on my Hewlett-Packard, and I didn't know what my frequency of A was, I could calculate it. Or I could probably work the other way around and calculate what B is, knowing what A is. As long as I know what either one is, and I see what the readout gives me, then I can determine the unknown. Also would give me a way to maybe make an adjustment one to the other, some ratio. Okay, so we've checked Frequency of A, frequency of C, ratio of A to B, period of A, we've done that. Let's take a look at the time interval of A to B. I'll have to figure out how we're going to demonstrate that. Alright, we are now set up in the time interval of A to B. And what I've done, without trying to set up something really Rube Goldberg to try and make this thing work, I've done something easier. I've got the signal from my 3320B coming in. It's a 50 hertz signal. I'm bringing it in on channel A. I'm connected AC. I'm working on the positive slope. So every time I get a positive cycle, I'm counting, triggering my unit to do the count, and then I'm connected common to channel B through this switch here. It's a separate or common. I'm making it common. And I've chosen the slope to trigger channel B to be the negative slope. So I go from positive to negative at a half cycle, at the half cycle point. So when the 50 hertz signal does the positive cycle, I've triggered on channel A and I start counting my number of microseconds or milliseconds, whichever it decides. And then when I start swinging negative, that's when I turn it off on channel B. And then I'm going to give the time interval between the two. Well, for a 50 hertz signal, the period is 20 milliseconds. So if I'm only going to trigger for half of the cycle and then shut off when I go negative, then I'm going to do that in 10 milliseconds. And by golly, that is what I'm being told right here, is I've got 10.00, roughly 0, we'll say 0, 10 milliseconds from the time that I triggered A through the positive half cycle of the 50 hertz signal to the time that it went negative. So it's saying half of 50 hertz cycle time is 10 milliseconds, which is exactly true. So the time interval of A to B is working. Now, if I really wanted to get some Rube Goldberg work here, maybe I would, I don't know, let's say we were monitoring the time it took for a little race car on a track to pass two photocells. And when I pass the first photocell, then I trigger A and I start counting the number of milliseconds till it hits channel B. And it'll tell me the time that it took to go between those 2 points, which it would then give me in the number of milliseconds, and perhaps I could convert that to speed. Might be something I do with it, or maybe I get fancier and I start working with lasers, and I start measuring the time that I emit a pulse from the laser till it's reflected off of a distant object and received again at another photocell. Perhaps that's something I could do. Anyway, time interval A to B works. And let's go to A gated by B. All right. Okay, well, now we've got the Fluke1953A connected so that we have 1 megahertz coming in on channel A. We are in the A gated by B position. And on channel B, we're using a gate with a a 0.5 hertz frequency coming in. I've chosen 0.5 hertz because it has a half cycle period of 1 second. So I'll be going high for 1 second and allowing myself to count what's coming in on channel A. I'm counting a 1 megahertz signal. So what I should see, right now we see ourselves incrementing up, but I'm going to reset ourselves when we go negative on the signal. All right, and then we're going to count. There's a megahertz. 1 meg. You'll see that there's 200 or 300 counts afterwards, something like that. That's because my generator generating the 0.5 hertz is only accurate to within a couple of decimal places, and then after that it's not. So we expect to see a little bit of slop afterwards, but we're reading the 1 megahertz. So we've created a counter counting 1 megahertz worth of cycles coming in for 1 second. Anyway, the preferable way to use the A gated by B would be to use just something that sent 1 pulse down the line for B, and during that 1 pulse period, then we count what comes in on A, and then we freeze the display. If we want to do that again, we send another pulse down. But because we're going repetitively here, I have to work with frequencies that are very slow so that I can reset the counter and display the results. So once a second works out, there we reset it, and we get the 1 megahertz. If I was to increase my frequency on channel B, then I wouldn't be able to reset and read the display. Let's say if we went to 5 hertz, it would be going way too fast. We'd be updating the display 10 times a second, so that wouldn't help. However, a pulse width equal to a 5 hertz positive pulse, then that would be a good way to do it. If I could just send 1 pulse down the line. All right. But we've proven that A gated by B is working. So really, I think we've walked through the entire unit, and we're going to wrap it up here. I did a test on the rear clock outlet, and it does put out a clock signal as long as we are powered on and not in standby. When we go into standby, which is when I turn this thing all the way counterclockwise and click it, I lose all power to the circuitry except for the heater elements and the oscillator. So we keep the master oscillator warm, don't allow it to get cold, and then we can turn back on, and power is applied to the circuit, and we're once again able to operate. So you wouldn't be able to use it as a benchmaster oscillator with it in standby mode. You'd have to have the counter on, and that would output a signal that could go to a distribution system. And using that distribution system, you could power the rest of your bench off of this one master oscillator. A lot of benefits to doing something like that. You can get your generator, your signal generator, to be in sync with your frequency counter to the same master oscillator. Then you can resolve frequencies between the two right down to the fraction of a hertz. So anyway, worth knowing, and bear with us. Well, as is my custom, I will be providing a set of starter test leads. These are coax to gator clip leads, kind of general purpose. Get you started. I hate to have anybody who gets a piece of my equipment to at least not have what's necessary to start out. So I'll give you the starter set, and also the user and service manuals on CD. So if you need a user guide to understand what you're doing with some of the functions, or if you need to do some service work in the future, you're not left in the lurch. So there you go. One really nice looking 1953A with the top of the line OCXO, with the 1 gigahertz add-on channel C card, and fully operated, tested for you, and we're all set. So thank you for listening, and happy bidding, huh?